In 1957, a young architect in Denmark won a competition. He was going to build one of the most famous buildings on Earth, before anyone knew if it could actually be built. He had drawn a roof made of curved white shells, rising off the edge of Sydney Harbour, like sails caught in the wind. Judges loved it, engineers were terrified of it, because nobody, anywhere in the world, had ever built a roof shaped like that. And for the next 4 years, the smartest structural engineers on the planet could not figure out how. This is not a story about a beautiful building. This is a story about a shape that broke mathematics, a genius who almost gave up, and a birthday cake that quietly saved one of the most iconic buildings ever constructed. Act 1. The shape with no formula. The architect was Jørn Utzon. The building was the Sydney Opera House. His winning design showed a series of dramatic curved roof shells sitting on a podium jutting into the harbour. Bold, unlike anything ever built. But here was the problem. Utzon had drawn the shells freehand. He'd taken a plastic ruler, bent it against a table, and simply traced the curve he liked. It looked incredible on paper. But an engineer can't build a curve that only exists as a feeling. Every shell in Utzon's sketches was a slightly different, undefined, free-form shape, meaning every single one would need its own unique formwork, its own unique calculations, its own unique everything. There was no repeating geometry to lean on, no shortcut, no pattern. Over Arup, the engineering firm hired to make this real, sat down to do the math, and hit a wall immediately. In the late 1950s, before computers could handle complex 3D structures, there was simply no way to calculate the stress and load paths on a shape that had no consistent mathematical definition. You cannot engineer a feeling. Act 2. 4 years, 12 failed attempts. Construction on the base of the building had already begun in Sydney. While back in Europe, Utzon and Arup's engineers were still trying to solve the roof. This is the part most people don't realize. They started building before they knew how to finish it. Over the next several years, the team tried everything: parabolic curves, ellipsoids, a dozen different structural schemes, each one either too expensive, too unbuildable, or mathematically unworkable. One of Arup's own senior engineers, a respected mathematician who had staked his reputation on one of the failed parabolic approaches, resigned from the industry afterward and never worked again. By 1961, 3 years after the plastic ruler sketch, there was still no answer. The client, the government of New South Wales, was losing patience. They floated the idea of bringing in a different engineering firm entirely. Utzon refused. He believed the solution existed. He just hadn't found it yet. Act 3. The birthday cake. Here's where the story turns, and it turns on something almost absurdly simple. During a visit to Utzon's hometown in Denmark, the two men were at a birthday party, and Utzon challenged over Arup to cut a cake into 17 equal pieces. Arup did it by first cutting the cake into 4 unequal parts, then dividing each of those into smaller, identical wedges, all cut at the exact same angle, just from different sized starting pieces. Every wedge, no matter its size, shared one identical angle. That single idea, many different sized pieces sharing one identical geometry, is what eventually cracked the entire roof problem. If every curved shell, regardless of its size or position on the building, could be described as a slice taken from the surface of one single giant imaginary sphere, then every unique shell suddenly wasn't unique at all. It was just a different-sized wedge of the same underlying shape. Act 4. The spherical solution. In 1961, after 3 years of failure, the team finally arrived at what became known as the spherical solution. Every one of the 10 shells on the Opera House roof, despite looking like different sail shapes from every angle, is mathematically a segment cut from the surface of the same sphere. 75 meters in radius, think of it like an orange. If you carefully cut different-sized wedges from one orange, every wedge is a different size and shape when you look at it. But every single wedge shares the exact same curvature, because they all came from the same sphere. That's the entire trick: one sphere. 98 identical ribbed segments, cut and combined at different lengths, could build every unique shell on the building. This solved 2 problems at once. First, because it was now one defined geometric shape instead of a dozen freeform curves, engineers could finally calculate the stress and load on every segment precisely. Second, and just as important for the budget, because every rib segment was now identical, construction crews could reuse the same formwork over and over. Instead of building brand new molds for every single shell, a building that had been mathematically impossible to define was now suddenly mathematically identical to itself, over and over again. The math itself was still brutal. The most complex piece of the roof analysis had over 100 structural joints, and on the computers available at the time, a single calculation could take nearly 4 hours to run, after nearly 3 weeks of preparing the input data by hand. Act 5. Building the unbuildable. With the geometry finally solved, construction crews could cast the same 98 rib segments again and again, in the same reusable molds, then assemble and post-tension them together into the 10 shells that make up the roof. The shells didn't just have to look right, they had to survive coastal winds. So Arup's team ran wind tunnel tests, calculating real load forces on those curved surfaces before a single tile went up. Then came the final layer. Over 1 million ceramic tiles, glazed to catch the Australian sun, applied across every curved surface of the roof, by hand, one at a time. The Sydney Opera House officially opened in 1973, 16 years after Utzon first won the competition, more than a decade after the roof had nearly stalled the entire project for good. Today, it's regarded as one of the most significant buildings of the 20th century, not just for how it looks, but for how it forced an entirely new relationship between architecture and engineering, one where the two disciplines had to solve the problem together, because neither one could solve it alone. Every impossible building in history hides the same quiet truth. The impossibility was never really about the impossibility. It was about not yet having found the one idea simple enough to make the complicated thing collapse into order. For Utzon and Arup, that idea wasn't a supercomputer. It wasn't a breakthrough in material science. It was a sphere. It was a cake, cut at a birthday party by two men who refused to stop looking for an answer that everyone else assumed didn't exist. Somewhere right now, another engineer is staring at a drawing that looks impossible to build. And the answer, when it finally comes, will probably look almost embarrassingly simple in hindsight. It always does.